piercing entire mountains, digging a tunnel under the sea, feats of civil engineering which pulverize all records. 3 sites have revolutionized working underground. Like at the Mont-Cenis in the 19th century. Driving a tunnel right through a mountain massif whose rock is incredibly hard. It's never been done before, yet it's made possible by a brand new invention.
An air-compressed drill, a kind of descendant of the pick hammer.
Its performance is a quantum leap in drilling. However, 140 years on, the tunnel has to be enlarged, an altogether new challenge for the engineers. How can they keep the walls from collapsing? The answer is a machine that digs with centimeter precision.
The laser checks the markers and tells the machine exactly how deep and how wide it has to dig.
Another feat long deemed impossible, a tunnel below the English Channel.
It was the sight of the century, like when 800 years ago they erected Notre Dame Cathedral.
It seemed a huge gamble to dig only 40 meters below the seabed and yet avoid the risk of flooding the site. The solution is stunning.
It's not just one tunnel, but 3.
The result is a world first, the longest underwater tunnel on Earth. A tunnel in the Alps holds another record. In 1965, the Mont Blanc Tunnel opens as the longest road tunnel in history. 50 years on, it also achieves the record of being the technically most advanced of its kind.
There are about 4,000 sensors.
How did the engineers rebuild a work more than 50 years old? What kind of machine was needed to replace entire sections of the tunnel?
It was a colossal effort, unique in the world. The old slabs were cut out, carried outside, and then the new ones were put in place.
3 examples of high-end engineering with unequaled challenges at the most spectacular sites. Be it oceans or mountains, we have always strived to overcome the obstacles nature has put in front of us. Tunnels have been among the first great achievements of our ancestors.
There are galleries dug by miners 40,000 years BC.
Be it Stone Age tunnels or the latest technological feats, there are hundreds of such sites the world over. However, the most spectacular of all, which has been in the spotlight of the international media and accumulated all sorts of records, is the tunnel under the English Channel. In 1994, for the first time, the British and French meet without having to board a boat or an airplane. The American Society of Civil Engineers classified the Eurotunnel as one of the 7 wonders of the modern world. To be able to get from shore to shore in 35 minutes was a dream conceived as early as 200 years ago. In 1801, a French engineer, Albert Mathieu Favier, imagines a tunnel with chimneys 80 meters high to allow for fresh air. An unrealistic proposal in view of a maritime zone with potentially tricky weather conditions. It takes until the end of the millennium before the project is considered feasible. In 1981, the governments of France and Britain give it the green light. 4 proposals come under scrutiny. One is a gigantic bridge with hundreds of stays. Another option envisages a combination of tube and bridge. Yet both sides agree on the tunnel, a project of 15 billion euros. Work is to begin on December 15th, 1987.
Before the construction proper, they did test drills in the seabed to analyze the different geological layers.
Samples brought up from several dozen meters indicate that there is a layer of rock at about 50 meters below the bed of the channel. Its characteristics are decisive for digging a tunnel. It's called chalk marl. It formed millions of years ago, when the dinosaurs still walked the earth.
It has two peculiarities. It's comparatively easy to dig, and it's impermeable.
The trajectory of the tunnel therefore has to follow this layer, as right above it there's grey chalk, which is much less dense. While grey chalk consists of 10% clay, the proportion in chalk marl is 25%, so it's less porous. Yet, there is another danger. If the miners dig too deep, they'll hit a layer of so-called gold clay.
That's to be avoided at all costs. Gold clay is a bit muddy and very soft. If the rotary shield digger were to have sunk into that layer, the whole adventure would have ended right then and there.
Thus, keeping exact track is paramount. The tunnel will run at an average depth of 50 meters under the seabed. If they get too close to the surface, millions of liters of water will rush in within minutes, meaning that the miners will have to follow the oscillations of the chalk marl layer. Digging under this premise poses no specific problem. Yet the ups and downs of the layer mean special trains capable of pulling their weight up long ascents are necessary. Trains that can tow trailers with 32 trucks in all, or more than 150 cars on every crossing, are envisaged. They'll set a record in the field of transportation. With tonnage on that scale, the engineers have to create new traction engines exclusively for the tunnel.
They designed hyperpower locomotives with 6 engines each and planned to have 1 locomotive at each end of a train.
Meanwhile, work has begun. Alas, before the actual tunnel can be dug, they must prepare 2 enormous vertical entries for the colossal rotary shield diggers. In Britain at Shakespeare Cliff, in France at Sangatte. Once they're completed, a quite exceptional machine can be loaded into each of them. The rotary shield digger is an invention that defies normal dimensions. A technological monster, a moving factory. It claws away at the rock, disposes of the debris, and sustains the walls at the same time. It's a Swiss Army knife, 250 meters long, so big that its parts have to be assembled piecemeal down in the pit. Inside the Colossus, there are control positions for engineers and technicians to monitor the monster. The steel giants will dig from both ends of the intended tunnel. Their shields weigh 50 tons each and are armed with 2 rows of dents, one of tungsten placed on top of the other dents, which weigh 80 kilograms. Thanks to this ingenious device, the dig will advance at a pace of 3 meters per hour. However, this performance must be achieved threefold, as there are 3 separate tunnels to be dug. One for the line from France to Britain, one for the reverse direction, and the third for maintenance. So what they need is 3 rotary shields on each side of the tunnel. And as the machines have to be replaced due to wear, there are 11 digger shields in use in the end, a mass of steel and machinery that tops the total weight of the Eiffel Tower, 10,000 tons. Yet they don't just dig. These masterpieces of technology more or less construct the tunnel all by themselves. relays of wagonettes carry off the ground rock back to the base of the pits, where they're reduced to mush by gigantic centrifuges.
There are huge rotating blades, and as chalk crumbles, all you have to do is add water until the whole mass is liquid enough and can be pumped away.
Millions of tons of chalk marl are thus dispensed of a bit further on outside the pits. It's such an enormous amount of material that on the English side it caused the most peculiar phenomenon.
We enlarged Great Britain. We created a stretch of land called Samphire Hoe, which is now a nature reserve for birds, plants, etc. It's all land gained from debris from inside the tunnel.
30 hectares of new land. Samphire Hoe is twice the size of the biggest stadium in France. The efficient extraction of rocks is one of the great advantages of a rotary digger shield. Yet the moving factories produce another essential element. They provide the installation of voussoirs. They put in place the separate sections which, when welded together, will constitute a watertight tube. 720,000 of them will make up the mantle of the tunnels. On the English, as well as on the French side, several square kilometers are needed to store them before they will be fixed underground. However, between the plates and the chalk, there's a gap of between 5 and 7 centimeters. It doesn't sound spectacular, but if water seeps into these cavities, the resulting pressure may endanger the stability of the tube.
There were teams whose sole task was to inject concrete into these voids to ensure the tunnel was watertight.
This protective mantle has been a major axis of maintenance ever since. Specialist workers continuously plug any fissures that may show up. With hundreds of trains rumbling through the tunnel, the seeping in of water is what engineers dread most.
As many as 400 trains pass every day.
In view of hundreds of passengers and thousands of tons of freight, measures to keep the tunnel watertight are indispensable. So when work began, the possibility of a major influx of water caused a good deal of concern. 2 sections of the tunnel demanded particular attention.
The engineers knew quite well that there were faults in the rock at the transitions between sea and land. These were the weak points, one on the British side and one on the French.
Thousands of litres of concrete are injected behind the voussoir. Apart from minor splits of 5 centimetres, there are cracks requiring a filling of several cubic metres. As long as the 3 tubes follow the hard and impermeable layer of chalk marl, there's little to no risk of an inundation of the tunnel. But what if there's a rupture in the crust of the earth? Seismic surveillance is taken care of by hundreds of sensors inside the voussoir. But up to now, tremors under the channel have been so small as to be practically indetectable. Yet, if there were a problem inside one of the tubes, engineers have provided for a bypass.
In that case, you can pass from one tube into the other, so there'll be no interruption of the traffic in the tunnel as a whole.
The engineers have planned for 2 gigantic crossovers. Tunnels within the tunnel.
8 kilometers from the English entrance and 12 kilometers from the French side, there are these immense cathedrals, the crossovers.
There, a train can be rerouted from its tube and enter the second tunnel, a rail crossing under a monumental vault. It's nothing unusual overground, Yet constructing one under the seabed is a challenge. A French engineer, Jacques Fermant, comes up with a solution. He proposes building an enormous hull to regroup the two tunnels. It's never been done before. 6 tubes of 200 meters are dug, then filled with concrete to solidify them. Together, they'll form a half circle.
It's made up of superimposed mini-tunnels.
Once the hull is completed, you just have to dig the cave underneath to link the tubes.
It was another historical first.
Yet the crossovers aren't the only links between the rail tunnels. There are other tubes needed for maximum exploitation.
Every 375 meters, there are so-called piston relief ducts, which link the rail tunnels.
They serve to evacuate the air, which builds up in front of an oncoming train.
You're inside a tube of 7.8 meters in diameter, so if a train comes at 150 kilometers per hour, there's an enormous compression of air. This air is pressed into the other tunnel via the ducts. Otherwise, the train's speed would be greatly reduced.
And speed is key to the entire project. Trains have to run at 150 kilometers per hour to achieve a frequency of 400 trains per day, which adds up to 26 million tons freight each year. It's yet another world record. However, to ensure that, constant maintenance is paramount. The wagons carrying trucks and cars are supersize, and as each train is 800 meters long, supervising their sensitive points requires a building of adequate proportions.
At 870 meters, it's the largest maintenance site ever.
The tunnel trains are inspected twice as often as those on conventional railroad nets. Maintenance and security are the top priorities for travel under the sea. After 6 years, work nears completion in December 1993. The two teams are a mere 100 meters apart from each other. The French rotary shield digger is stopped. Its hundreds of parts are dismantled and taken out of the tunnel. The British have opted for another solution. Their Colossus takes a turn to the right and is immobilized for all time. Yet one last question remains. Are the digs from each side in line? And what if a digger shield has proceeded too high? In the 1990s, GPS can't help. At this depth, no satellite signal is strong enough. So the British engineers send forth a probe. A telescopic pole bores its way through the rock. Finally, after several dozen meters, there's the breakthrough. They've met the French tunnel spot on.
We were right there, a mere 40 centimeters to the side.
On December 15th, 1993, at 12 minutes past noon, Philippe Cosette shakes hands with his British counterpart, Graham Fagg. The images are flashed around the world. The longest undersea tunnel in history is completed. Today, its users are 85% British. The Eurotunnel is a physical link between France and Britain. Its construction has become a benchmark in engineering. Yet, there was a precursor, which 150 years before, forever changed the technology of tunnel building. The tunnel of Mont-Cenis in the Alps retains a special place in history. In the 19th century, it seems a huge gamble. How do you pierce a mountain massif over 13 kilometers, 6 times the length of the Champs-Élysées Avenue in Paris? A tunnel traversing the Alps to link France with Italy. It's a breathtaking proposal. The obstacles are literally towering. Yet the commercial rewards promise to be staggering. As for a site, the powers that be opt for the Maurienne Valley.
It's one of the Alpine valleys which link the city of Lyon with the industrial north of Italy, Milan, Turin and so on.
The best option for trade via a tunnel is transporting goods by train. First, however, some political peculiarities have to be taken into account. When work begins in 1857, the Duchy of Savoy in the Western Alps is still a possession of the Kingdom of Sardinia, one of the many states which soon will constitute the future Italy.
That means work began on a territory that was 100% under Italian control, and only after Savoy was ceded to France in 1860 can we speak of a proper French part. It's unique to have a project which starts in one country and ends up in 2 with different nationalities.
A political tangle which isn't conducive to speeding up work. It takes the miners more than 15 years. Not least because they have to dig by hand.
They managed 40 centimeters a day, which is extremely slow.
The slow advance also results from a total lack of knowledge about the kind of rock the miners encounter. Soft, hard, porous. Conditions vary constantly. Today, before work even begins on a tunnel, geologists reconnoiter the environment by using probes.
You dig a small pre-gallery to see what you will encounter.
Back then, there was surprise at almost every layer. If the rock proves too hard, there's only one way of advancing: to blow it up. Yet, resorting to gunpowder is fraught with danger. At the time, the workers still had a lot to learn. It's a most risky job.
They faced all sorts of imponderables. There were dozens of fatal accidents.
The use of gunpowder causes rockfalls which slow down the work. The natural vault has a tendency to subside or to collapse altogether. Digging proceeds at an agonizing pace. Contemporary specialists estimate that it will take at least 30 years to finish the tunnel. Exasperated, British merchants who are eager to transport their goods overland to northern Italy hit on an astounding idea. They proposed building a railroad across Mont-Cenis at 2,000 meters above sea level. While the tunnel is still under construction, the Mont-Cenis Railway Company intends to operate a regular train. Alas, the long-winded ascent is often blocked by snow or avalanches of loose rock, which reduce speed to a mere crawl. The venture costs investors several £1 million. In the end, it's a financial disaster. This is also largely down to a technological revolution. A local engineer, Germain Sommelier, has invented a device which will prove a watershed in tunneling. The ingenious new tool is based on using compressed air to drive a drill. It will transform work underground for decades.
A 19th century drill resembles a harpoon. It's 3 to 4 meters long and pierces the rock. To accelerate work, which, as some said, would never end, Sommelier provides drills with a percussive power
previously unheard of. And what's more, he procures the required energy directly from the environment of the tunnel, from its abundance of water. A wheel driven by streams deviated from the mountain pumps air into watertight pipes. Thanks to a flap valve which closes automatically, the air is compressed and stocked in huge cylinders.
Thus, the air can be sent to the drills by a system of conduits.
When the valves are opened, the air shoots through the pipes into the interior of the tunnel, where its power is liberated and feeds up to 4 drills at the same time. With a pulse of 50 beats per minute, the machine is capable of drilling holes several dozen centimeters deep. The miners then ram in their explosives. Thus, the detonation will take place deep inside the rock, instead of at the face of it. A much more efficient way of blowing up things. Sommelier's machine allows several meters to be advanced each day. The new technology pulverizes all existing records in digging. Yet the new method comes at a price. The multitude of explosions cost the lives of more than 50 workers.
At sites like this, back then, safety was non-existent.
Working conditions are aggravated by clouds of dust, which are blown back into the tunnel after each explosion. The dust penetrates into the lungs and blinds the workers. No one can stand this for long. Germain Sommelier must adapt his machine, and he does, with another brilliant solution.
He used the compressed air to drive ventilators in order to ameliorate the air in the tunnel.
The engineer also inserts small openings in the machine itself, which allow the air to pass and thus clear the workspace of dust. Now the miners can continue at a much more stable rhythm. The schedule for the construction of the tunnel is greatly reduced. Sommelier's invention shortens the allocated time of 30 years by almost half. The tunnel opens in 1870. It's a feat that causes a buzz all over Europe. Only the contractors of the Mont-Cenis railway company don't join in the jubilations. Their tracks have been made redundant by compressed air. Due to the tunnel, trade between France and Italy surges. The construction will prove a success for more than a century. With the arrival of the new millennium, however, profound modifications are required. The transit of thousands of heavyweight trucks between France and Italy calls for an alternative solution.
Generally speaking, trucks aren't too welcome in the Alpine valleys.
Their exhausts pose a major problem. To maintain traffic through the Alps, the powers that be decide to put the trucks or their containers on trains. A splendid idea, except that the tunnel is too low. Enlarging it is a daunting prospect.
To augment the size, you either have to raise the vault, or you must lower the base.
Before the oversized trains could safely pass through the tunnel, the present base has to be dismantled and taken out. The option of hacking away at the walls and the ceiling seems problematic. The tunnel may simply collapse. However, digging up the floor is easier said than done. How do you lower the base sufficiently and provide a safe bed for the new rails? A machine capable of doing that doesn't exist. Yet.
So, they invented one.
In 2007, a French company presents an extraordinary tunneler, the D-Rocker. With a weight of 50 tons and a wheel fitted with massive teeth, the D-Rocker is an extremely efficient device. Its forward part bites into the rock and digs up the floor. Yet, before it can be let loose, the ground has to be prepared.
One of the tracks was completely dismantled. The rails, the ballast, the sleepers.
Once the way is free, the D-Rocker can go about its job. It's guided by lasers, which keep it on track and also relay data on the soil ahead. It proceeds at a speed of between 40 and 60 meters per day. To keep the wheel from overheating, its teeth are sprayed with water. The debris is transported to the back of the Goliath.
The rubble is taken out by a conveyor belt.
Thousands of cubic meters of materials are thus evacuated, and the apron is lowered by 70 centimeters over the entire 13.6 kilometers of the tunnel. In 2011, the first trucks roll onto the platforms, enabling the transport of their cargo to be continued by rail. Each day, more than 30 trains enter the Mont-Cenis tunnel. Yet, there's one issue left unsolved. The tunnel doesn't comply with modern safety criteria. Safety has become a major concern in the field of transport. A decision is inevitable. The Mont-Cenis tunnel has had its day. It will be replaced by the most modern tunnel ever built. To link Lyon to Turin, a stretch of 57 kilometers will be dug underground. The equivalent of 285 TGV high-speed trains lined up behind each other. It's a tunnel of exceptional length, and it will be right under its predecessor.
It passes through the same alpine massif, albeit 800 meters deeper.
The future tunnel is intended for goods and passenger trains. Work begins in 2016. It's supposed to be completed in 2035. It will have everything the tunnel of 1870 lacked, such as ventilation pits to face a worst-case scenario, a fire in the tunnel.
They'll serve to keep one of the tubes free of smoke and bring fresh air into the other tube, which can then be used as a refuge for passengers.
The pits in themselves require state-of-the-art technology. First, the teams drill a hole of a few centimeters in diameter from the surface down into the tunnel. A telescopic arm will then rotate a cross-like device fitted with teeth in the cavern below. The cross then grinds its way upwards, while the loose rocks drop down to the bottom.
From time to time, drilling must be halted to take out the rubble. For the workers, this is the most critical part.
Thus, a diameter of 4.3 meters can be achieved. There'll be 3 more pits close to the first.
There aren't many people in the world capable of doing this kind of work.
The new tunnel will relieve the old subterranean passage, completed in 1870. The Mont-Cenis tunnel will keep pride of place as the first ever traverse right through the Alpine Massif. Yet, not far away, there's another legendary tunnel. The Mont Blanc Tunnel. It proved a completely new challenge for engineers. Since it was intended for exclusive use by cars and trucks, it had to be much larger than a railroad tunnel. Yet would it be possible to pierce a massif with a tube 10 meters high and 8 meters wide? In the late 1950s, no one could tell.
It was a true adventure. We didn't know what we'd encounter once we were inside the mountain.
It will be a project to beat all records. The longest road tunnel in the world. An amount of explosives never used before. With newly developed drills to achieve the envisaged height and width. In 1959, work begins. The new passage through the Alps reflects the booming economy of the 1960s.
Earlier on, any crossing of the Alps was a veritable expedition, with caravans of horses and creaking carriages. With the Industrial Revolution and the expansion of international relations, however, the Alps became a real problem for the exchange of goods.
Yet before work on the 11-kilometer tunnel can begin, its route has to be fixed. And as there's no GPS back then, it means resorting to triangulation to produce an imaginary straight line with the peaks of the surrounding mountains as reference points. And so, there's only one way, and that's up.
There were mountain guides to help the surveyors. The campaign to get the necessary measurements took several months, not just a few days. And often the weather conditions were anything but favorable. It took guts.
At 3,500 meters above sea level, mountaineers and surveyors take great risks to establish the direction of the tunnel.
2 guides lost their lives.
To pierce the highest massif in Europe with its granite of extreme density and hardness, French engineers develop a special machine, the Jumbo. An enormous movable scaffold weighing several hundred tons, allowing 25 workers to operate 16 drills at the same time. Their percussive power permits explosives to be placed 4 meters deep inside the rock.
You press the button and clear the rubble away.
Over the next 44 months, the Jumbos on the Italian as well as on the French side drill more than 400,000 holes. 1,200 tons of explosives will be detonated inside them.
When digging a tunnel, water is a recurring problem.
We're talking of 1,000 liters per second at times.
The water comes from a glacier right above. In springtime, the rivulets of melted ice can turn into waterfalls at certain points. Yet, it's a problem the engineers have anticipated. The tunnel isn't truly horizontal.
It ascends and descends, causing the water to flow away.
Without these slopes, the miners would be engulfed by thousands of cubic meters of water. But the constant humidity undermines the stability of the tunnel walls. To keep them from collapsing on top of the workers, the engineers decide to install voussoirs, sections of concrete which will form a protective tube inside the tunnel. Yet, with 2 kilometers of rock above, additional precautions are obligatory.
They put in a kind of iron roof, steel plates that kept the vault from collapsing.
It was a fairly new concept. The vault was literally tacked into the walls.
With its 235,000 bolts, this system of consolidating the surrounding rock allows the miners to continue without having to fear a collapse of the vault. Yet the further they advance, the more difficult it becomes to breathe. The problem is solved by conducts, great corridors above the future traffic tube. They will bring in fresh air from the entries. This installation is still in place 50 years on. Today, 5 gigantic ventilators of 2.8 meters in diameter at each end of the tunnel provide for a constant airflow. In 1960, the system is far less sophisticated. However, after 3 years of tunneling, French and Italian miners are only a few meters apart from each other. On August 14, 1962, at 11:31 a.m., they join hands after having blown up the final blocks of granite. The two sections of the tunnel line up almost perfectly.
The deviation from the theoretical axis was a mere 13 centimeters.
3 more years are necessary to complete the retaining work, to coat the lanes, and to install a signal system. On September 15, 1965, the first automobiles enter the tunnel. Each year, hundreds of thousands of cars and trucks pass through the longest tunnel of its time. It's considered an emblematic link between two nations, until one fateful day.
March the 24th, 1999.
On that day, at 10:47 a.m., a Belgian truck enters the tunnel. Its cargo of margarine catches fire. The driver is forced to stop. The heat amounts to that of a tanker in flames. At 10:54, the alarm is raised. The toxic fumes spread through the tunnel, claiming 39 lives. The cause is quickly established. The air system back from 1965 is disastrously insufficient. It must be brought up to date. The fire forces engineers to revise the know-how of several decades of tunnel building. The Mont Blanc Tunnel will be closed for 3 years. The French-Italian company running the tunnel embarks on nothing less than a rethink of the entire project.
In terms of technology and surveillance, it's an entirely new tunnel.
Analysis of the fire focuses on the problem of fumes. How can they be extracted as quickly as possible? Irrespective of where they may occur along the 11 kilometers of the tube, the engineers decide to create aspiration points at regular intervals. Thanks to ventilators up in the tunnel, the fumes will be blown towards traps, then sucked into airtight shafts under the lanes, and thus evacuated to the nearest exit.
The algorithms of the system allow the ventilators to be activated in both directions.
4,000 sensors are distributed along the tunnel, providing the control center with thousands of data in real time. One of the most closely monitored of them is the opacity of the air, as this signals the presence of smoke. There are additional ventilation systems at the entries of the tunnel. Their function is not to counter the consequences of a fire, but to anticipate a climatic feature of the mountains.
We have to watch out if there's fog up on one of the peaks. It must be kept from entering the tunnel to guarantee visibility for the drivers.
Apart from the air, the entire construction back from the 1960s is under constant vigilance. To that end, 11 kilometers of optical fiber has been implanted in the road surface. It's ultra-sensitive and registers all movements in the coating.
Any deterioration of the cable results in a degradation of the signal. And according to the quality of the signal, we can tell the exact amount of deformation.
An interruption of the signal means that the road surface is no longer stable and has to be replaced. Yet, how do you replace entire road sections of several tons each without halting the traffic for days? The engineers have to invent an unprecedented machine.
It was a colossal enterprise, unique in the world. We had to extract the old sections, bring them outside the tunnel, and then install the new ones.
At night, on a 600-meter stretch of the tunnel, the coating is lifted from its bed 6 centimeters deep in the floor. Then the sidewalks and the great plates covering the walls have to be taken out. The special machine lifts a 6-meter plate of 2 tons, then pivots it, puts it on a trailer, which then exits the tunnel.
Turning the plate is the most critical part. It mustn't break or hit the walls.
The machine then receives a new road section and lowers it into the gap. It's a process which gains worldwide acclaim, especially since traffic in the tunnel can go on without interruption.
On average, we have 1,600 heavy vehicles per day.
The frequency could even be increased, but for safety reasons, circulation is limited.
We don't allow a random flow of traffic. We have a system that sets the cadence at 1 vehicle every 8 seconds. That's the time a car needs to cover 150 meters at 70 kilometers per hour.
Thus, safety distances are ensured. To dissuade those who like to step on it and don't respect the 12 minutes allocated for one traverse, there are 6 radars within the tunnel. They also calculate the average speed of each car. Those who exceed the speed limit will face the policemen stationed at each end of the tunnel. The Mont Blanc Tunnel, with its 200 cameras and heat sensors at its entries, has become one of the safest underground constructions the world over.
It's a model for the European Directive of 2004 regulating safety procedures in tunnels.
Yet regulations for the tunnel don't stop there. Brand new technology will be implanted. It's called platooning.
Imagine 4 or 5 trucks following each other fairly closely at a distance of about 10 meters. The one in the lead, which we call the pilot truck, will steer the entire convoy.
The trucks will communicate with each other, but also with the tunnel. There'll be data on dangerous cargoes, on drivers who haven't kept to their mandatory rest, and even on the tire pressure of individual vehicles. The tunnel will keep an eye on everything that enters it. The inventions serving the Mont Blanc Tunnel are scrutinized the world over. Just like the latest brainchild of Elon Musk, a rail tunnel with a vacuum inside and without oxygenation, with an air cushion to avoid all friction for the train. Freed of all resistance, it's intended to run at 1,000 kilometers per hour. In France, a test range of 300 meters has already been built to evaluate similar projects. Technological evolution still seems to have a lot in store for us. If these projects will once see the light of day and change our daily lives, it's because their precursors have paved the way by incredible exploits. Such as piercing the Alps for the first time, inventing machines never seen before, digging the tunnel of Mont-Cenis, linking France and Great Britain by establishing the record for the longest undersea tunnel. The Eurotunnel has been a success ever since. Digging the longest road tunnel in history through the highest mountains in Europe. The Mont Blanc Tunnel has become a reference work of its kind. All these ventures are witness to the ingenuity of civil engineers and their willingness to overcome any obstacle. Tunnels will continue to serve as links between people and as spearheads of innovation.